Generative models are a popular class of tools in machine learning used to create highly realistic outputs such as images or speech.
Two types of generative models you may have heard of that we'll use in our project are variational autoencoders and generative adversarial networks. These models map points in a so-called latent space to realistic output, as we can see in the autoencoder architecture below, with this gray box representing the latent space and the reconstructed image being our output. The points in the latent space still represent the original input, but exist at a much lower dimension. Furthermore, their values don't directly map to the input, so it can be difficult to decode their representation. Each of these images in the figure below to the left is the output from our model corresponding to a different point, and each looks realistic. But what if we want to generate a very specific output, say speech with a particular accent, or a face with specific characteristics, such as brown hair or blue eyes? Finding points in the latent space that correspond to these particular outputs is very difficult. Even worse, in popular models, the latent space dimensions can often reach 256, and as you can imagine, it's not possible to specify these manually. To solve this problem, we borrow ideas from popular psychology. A common problem in human studies is that people lack the ability to consistently quantify their preferences. Paired comparisons are one common strategy to overcome this. It is much easier to say I prefer item A over item B than to give consistent numerical scores for how much I like certain things. The Davenport and Rozell labs have developed algorithms to localize points based on these types of paired comparisons. The user is given a series of two choices and simply decides which one is closer to what they want. In the background, the algorithm continues to narrow down towards an ideal output. The model is accurately depicted in the figure below, with the user obviously choosing the cookies and the pie. The model uses features from the user's choices to determine an ideal snack for the user, in this case, a sweet and chewy brownie. Our project applies algorithms for learning from paired comparisons that were developed by the Davenport and Rozell labs to generative models. Here I'll explain how these algorithms work intuitively. Each of these point pairs represents a choice that the user must make, say between two snacks as seen in the previous slide, or two models of shoe, for example. First, we ask which of the two green point items the user prefers, which tells us that the ideal point for this user is somewhere on the right side of the green bisecting hyperplane. Obviously, they chose this point on the right. We then perform another paired comparison, which next reveals that the ideal point is again located on the right of this yellow bisecting hyperplane. As you can imagine, as we collect more comparisons, we can localize the ideal point with greater accuracy and eventually reveal the ground truth or ideal point for this user. So how does this all tie into our problem of finding a latent point that corresponds to a desired output? Our proposed solution is to implement the paired comparison approach to navigate this abstract latent space. It is very difficult to interpret the relationship between the latent space values and their outputs, and so paired comparison helps us navigate this region. There are far too many factors to manually analyze, and so we interpolate these incomprehensible values into a concrete image or output. These visuals highlight the complications of understanding the latent space. As you can see, this embedding is complex even in 2 dimensions. In a latent space with hundreds of dimensions, it would be almost impossible to localize a specific point without this visualization approach. Several applications we have explored revolve around human preference and decision, including graphic design, game textures, and fonts, as well as allowing users to generate specific shoe models or even songs. We have also discussed employing our approach in generating speech or text. One impactful potential application we'll talk about later is augmenting existing datasets for future machine learning model training and/or testing. This could be extremely effective, especially in the medical industry.
So to test our proposed approach, we first use a well-known and pre-labeled MNIST digit dataset. So if you're unfamiliar with machine learning, you can think of this dataset as the equivalent of a Hello World program. So although we envision more complex applications than this digit dataset in our pair comparisons algorithm, we actually are using this to test whether or not our method works as expected or not. And we can test this by seeing if we can allow a user to generate any desired image that comes from their head using pair comparisons. You can actually see a demo of our pair comparison algorithm in action. So in this demo, the user desires to localize a point in latent space corresponding to the digit 9. So we have the user go and choose between 2 different images. And each image is actually randomly generated in latent space, so randomly sampled out of the entire space of digits. So if he desires the image that's generated on the left, he'll input a 1. So for instance, if it's a 9 or looks similar to a 9, he'll select a 1. Likewise, if he wants the image shown on the right, he'll input a 2. And if neither image corresponds to one he wants, so for instance a 1 and a 6 are shown, he'll just skip that comparison by clicking enter. So in this experiment, we performed 25 comparisons, attempting to produce the image 9. So you can probably see that after every comparison that the user makes, there's a small gallery of about 100 images showing up after each image. So this will be described later in the slides. Its main purpose was for debugging, but the most significant takeaway from this demo comes at the end of the video. So here you can see that after performing 25 comparisons, we have finally localized a point in latent space. And once we generate an image corresponding to that, like you can see, it is a 9. I did this without knowing anything about the latent space while I was making these comparisons. I was just picking the numbers that looked more like a 9 to me. The promising results of this led to further experimentation. The next test we performed was a more rigorous test to give us confidence that we could reliably localize a point in latent space. And the way we did this was by creating a visualization in 2D space. This visualization is known as TSNE. And in this experiment, we take that localized 9 from the earlier demo that we used with 25 comparisons, and we plot that latent point with other points that are in the TSNE visualization. So as you can see from this image, the distance of the 9 that we localized and the distance of that to other points, it actually correlates to the Euclidean distance of those other points. And so one can see that the Euclidean distance, even when visualized in 2D space, correlates strongly to visual similarity. And you can see that through this TSNE image. You can see their digits such as 1s, 7s, 4s, 8s, and they're all in their own little clusters. And the 9 is its own little cluster with 4s and 7s, two images that look very similar to that. So with this experiment done, we have shown that we can actually localize a latent point that corresponds to a desired output image with 25 comparisons, which is relatively few. And this actually is a gallery of images that we showed earlier in the demo. So as you saw earlier in the demo, a gallery of 100 images would show after every comparison that we made. And like we stated earlier, it's been composed of digits that have been randomly sampled from latent space. Now, after every comparison, our model is able to estimate an ideal point of the user. So for instance, after every comparison I make, the model has a better idea of the 9 that I want to generate. So this model takes this gallery of random images that we generated, evaluates the Euclidean distance between those generated points and the ideal point that it thinks that I'm thinking of, and then it fades it proportionally to that distance. So in other words, digits similar to a 9 will be kept, while digits less similar to a 9 will be more faded. So one can see that after a few comparisons of these remaining digits, most of the digits remaining look like 9s. Something similar to a 9, such as a 4 or a 7, may show up as well. But in general, the least faded images are 9s. So this experiment actually only further shows the fact that our pair comparisons algorithm is effectively able to generate a desired output.
We next implemented our latent space localization framework with StyleGAN2, a state-of-the-art generative adversarial network trained to generate realistic human faces. Its latent space has 256 dimensions, which is significantly larger than that of the VAE we used with MNIST. This means that many more comparisons would be required to get good results, so we turned to more sophisticated methods, which strategically choose points in each comparison to maximize information gain. Here we applied an algorithm from a recent paper by one of our lab members. This method generated the comparisons you see on the left. We went through 15 such comparisons, and in each, selected the image that looks more similar to the target on the right. Our framework yielded the result which qualitatively appears to be pretty close to the target image. Considering our progress with obtaining desired images from generative models, the next logical step would be to conduct a user study to quantify the advantage of our method. We would first ask volunteers to manually tweak latent vectors for some generative model like StyleGAN2 to obtain an image similar to some ground truth. Then we would allow them to perform a series of paired comparisons using our framework to obtain the same result. A possible performance metric could be how long it takes volunteers to obtain the target image using each method. Further, we would like to extend our model to domains beside the images, such as speech, music, and text generation. Additionally, we believe that applying our paired comparisons framework can help further the scientific understanding of the latent space of GANs and VAEs. Our framework will allow researchers to characterize specific traits of latent space and better interpret how they get affected by changes in network architecture. Finally, one of the most significant problems in machine learning is obtaining the large quantities of data necessary to train accurate models. Data augmentation is one approach to extend existing data to improve model performance. Data augmentation is primarily used in training classifiers. There are many examples of which class are typically required to achieve high accuracy. However, in some applications, we don't have access to enough samples of a particular class. This example from medical imaging shows two types of CT scans, contrast and non-contrast. They are used to train model which will determine various types of aneurysms in the image. The former is more prevalent in labeled training datasets, but the latter is more common in the real world. Thus, the resulting model does not perform well with non-contrast images. We believe our framework could be used to perform data augmentation to solve this problem. We could train a generator using both contrast and non-contrast images and then use our framing to find a region of latent space corresponding to non-contrast images with known aneurysms and use those synthetic images to train the model. Now, let's summarize the work we've covered in this presentation. We started with a generative model, a neural net that can take vectors in latent space and translate them into images. However, in many applications we want an output with some specific features, but we don't know which point in latent space corresponds to our desired image and lack the vocabulary necessary to describe those features in the latent space. To solve this problem, we turn to known spatial localization methods using paired comparisons. Additionally, our framework allows generative models to be useful in a much broader set of applications and could be used in a data augmentation scheme to improve many machine learning models.